In this video, we will analyze the response of an RC circuit when the input is unipolar voltage pulse train. Consider an RC circuit. R is equal to 1 kilo ohms, capacitor is 1 microfarad, T on is equal to T off is equal to 5 milliseconds. This is the input voltage that we are feeding to the RC circuit. The voltage level is 5 volts. Now, since R and C are in series, the capacitor will charge and discharge according to the applied voltage. Let's find out how the voltage across the capacitor looks like between 0 to 5 milliseconds. The voltage across capacitor can be calculated as V in into 1 minus e to the power minus TR by RC. TR here is the real time. From KVL, we know that V in is equal to VR plus VC. Hence, VR is equal to V in into e to the power minus T by RC at t equal to 0 to 5 milliseconds. Now, from 5 milliseconds to 10 milliseconds, the voltage source is replaced by a short because it is 0. Hence, VR is equal to minus of VC because V in is 0. And the voltage across capacitor can be calculated using the following equation. T start here is 5 milliseconds. Since we are considering the window of 5 milliseconds to 10 milliseconds, T start will be 5 milliseconds. If we are considering 10 milliseconds to 15 milliseconds, then T start will be 10 milliseconds. TR is the real time. And voltage across resistor can be calculated as follows. Since R and C are in series, same current flows through the circuit, which is equal to voltage across resistor divided by R. Now let's see how the voltage across capacitor between 0 to 5 milliseconds looks like. If we consider 5 intermediate points before 5 milliseconds, that is 0, 1, 2, 3 and 4 milliseconds, and plot it, we can see that the nature of the voltage across capacitor is increasing exponentially and can be calculated using the following equation. When we plot these values, we can see that the nature of the graph is exponentially increasing. And at 5 milliseconds, it gets charged up to 4.96 volts. Now, between 5 milliseconds to 10 milliseconds, the voltage source is replaced by a short circuit and the voltage across capacitor can be calculated using the following equation. Now, between 0 to 5 milliseconds, the voltage across capacitor gets charged to 4.96 and that is multiplied with this exponential factor. And we can see that on plotting these points, the voltage across capacitor is exponentially decreasing. Now, this is how the voltage across capacitor looks like for one cycle of on and off time. We saw that in the presentation, we considered 5 intermediate points between 0 to 5 milliseconds. Here in the Excel sheet, the voltage across capacitor is calculated for every 200 microseconds so that we can capture the accurate behavior of VC. On plotting this, we can see the nature of voltage across capacitor versus time. Let's look at how voltage across resistor looks like. Can be calculated using the following equation as discussed earlier. And on plotting these values, we can see that the voltage across resistor starts from 5 and decreases exponentially as the capacitor charges during on period, that is between 0 to 5 milliseconds. And during off period, the voltage source is replaced by short and voltage across capacitor can be calculated using the following equation. T start here is 5 milliseconds. TR is the real time. Now the voltage across resistor starts from a negative value, which is approximately minus 5 volts and increases exponentially towards 0 while the capacitor discharges. This is how the voltage across resistor would have transformed during one cycle of on time and off time. Like we saw for voltage across capacitor, similarly let us see for voltage across resistor considering intermediate points for every 200 microseconds. Now we can see the behavior of voltage across resistor. This is how the voltage across capacitor and voltage across resistor would have transformed. And this is the input voltage that we are feeding, which looks like this across capacitor and which looks like this across resistor. Now let's look at the current flowing through the circuit, which can be calculated using the following equation. And on plotting this, we can see that the nature of the current flowing through the circuit is similar to the voltage across resistor, because the current flowing through the circuit is equal to voltage across resistor divided by R. Now similarly, between 5 to 10 milliseconds, the current flowing through the circuit can be plotted as follows. Now this is how the current flowing through the resistor looks like between 0 to 10 milliseconds. Now, if we can observe the current flowing through the resistor here, it looks similar to voltage across resistor, because IR is equal to VR by R. Now, let's look at the case where on time is much greater than off time. On time is 3 milliseconds and off time is 2 milliseconds. Voltage level is 5 volts. This is the input that we are feeding to the RC circuit. Now, the voltage across capacitor and resistor can be calculated as follows. TR is the real time here. Now, between 3 milliseconds and 5 milliseconds, VC and VR can be calculated using the following equations, and IR is equal to VR by R. Now, let's consider 6 intermediate points here and observe the voltage across capacitor. Now, between 0 to 3 milliseconds, the input voltage is equal to constant 5 volts. This is the on period. And the voltage across the capacitor during this on period can be calculated using the following equation, and the values are as follows. Now after 3 milliseconds, the input drops to 0 volts and remains 0 volts constant up to 5 milliseconds. During this period, the voltage across capacitor can be calculated using this equation, and we obtain the following values. Now on plotting this, see that between 0 to 3 milliseconds, it is increasing exponentially, and as soon as the input voltage drops, the voltage across capacitor starts decreasing exponentially. Here in the Excel sheet shown, the voltage across capacitor is calculated for every 200 microseconds. Plotting it, we can see the nature of the voltage across capacitor. The same voltage across capacitor for the next cycle, which is from 5 milliseconds to 8 milliseconds, it can be calculated using the following equation. And voltage across resistor can be also calculated using the following equation. And between 8 to 10 milliseconds, the input voltage becomes 0, and hence voltage across capacitor and resistor can be calculated as follows. Now here we can see that between 5 to 8 milliseconds, the input voltage 5 volts is available, and after 8 milliseconds, the input voltage has dropped to 0. Now on plugging in the values shown in the respective equation, we can calculate the voltage across the capacitor. Now let's see how the voltage across resistor looks like. Between 0 to 3 milliseconds, input voltage equal to 5 volts is available, and voltage across resistor can be calculated using the following equation, and the values are obtained using this equation. And between 3.1 milliseconds to 5 milliseconds, the input voltage drops to 0, and hence it is replaced by short, and the voltage across resistor can be calculated as follows. Now on plotting these values, we can see that the voltage across resistor looks like this. On considering 200 microseconds intermediate points, here we can see for every 200 microseconds, the voltage across resistor is calculated, and this is the real time, and this is the calculated voltage across resistor using the formula, which is equal to V in into e to the power minus t by RC. RC is equal to multiplication of R and C. Now on plotting this, we can see the nature of the voltage across resistor. Now let's look at the current flowing through the circuit. Since R and C are in series, same current flows through the circuit. which is equal to VR by R, and it looks similar to the behavior of voltage across resistor. We can see that the current flowing through the circuit is plotted and it looks similar to voltage across resistor. And its formula is VR divided by R. Now on considering 6 intermediate points between 0 to 5 milliseconds, the voltage across capacitor equations are as follows. Between 0 to 1 milliseconds, the input voltage of 5 volts is available, and between 1.1 to 5 milliseconds, the input voltage drops to 0. And on plotting these values, this is how the voltage across capacitor looks like. The voltage across capacitor is calculated as follows. Between 0 to 1 milliseconds, which is equal to V in into 1 minus e to the power real time by minus real time by RC, which is the time constant of the circuit. And on plotting this is how the voltage across capacitor looks like. Now for the second cycle, the voltage across capacitor can be calculated as follows, and the voltage across resistor can be calculated using the following equation. Now here there is an additional term because during the first cycle, that is between 0 to 5 milliseconds, the voltage across capacitor would have charged to some value that needs to be added by multiplying with an exponential factor, which is the initial voltage of the capacitor. And between 6 to 10 milliseconds, this is the discharging equation for the voltage across capacitor. And VR can be calculated as follows. Now let's look at how voltage across resistor looks like. Between 0 to 1 milliseconds, voltage is available, and between 1 to 5 milliseconds, it is replaced by short. On using these equations and obtaining the following values, on plotting it, we can see that voltage across resistor looks like this. On calculating voltage across resistor for every 200 microseconds, this is how the graph looks like. It starts from 5 volts and decreases up to minus 5 volts during on time from 0 to 1 milliseconds, and during off time 1 milliseconds to 5 milliseconds, it starts from minus 5 volts and reaches up to 0 volts while the capacitor discharges. Since R and C are in series, the current flowing through the circuit will be equal to VR by R. Now the nature of the graph looks similar to voltage across resistors graph. Plotting the current flowing through the circuit, we can see that it is similar to voltage across resistor, and it is calculated by dividing VR by R. Now let's simulate this and check. Here I have considered a case where on time is equal to off time, which is equal to 5 milliseconds. On simulating this, we can see the nature of the voltage across capacitor, voltage across resistor, current flowing through the circuit. So the capacitor's voltage exponentially charges towards the pulse voltage during on period and discharges during off period, and the resistor's voltage starts at maximum during pulse transition and decays exponentially following the capacitor's behavior. If the time constant of RC circuit is comparable to input pulse width, then it will not resemble the behavior for unipolar voltage pulse train input. Thank you for watching this video.